good. So the question always is, what's the last thing in your notes from last time? Anybody? Yeah.
Angle theta to horizon from the top of a mountain of height h.
Good. I'm going to try to make an assignment out of that. So, but we're going to review the shape and size of Earth, and in fact, the shape we're going to assume this time. Actually, come back to it. So this is just a quick review, and you guys who weren't here are in good shape for this. So the first argument we're doing is if we know it's a sphere and we're Eratosthenes, this is a very nice symbolic picture, which I'm going to label here. So that's the Earth in profile. These are rays of the sun that we're assuming are parallel, whether or not they are, it's close enough, okay? And this here is a point on June 20th in Aswan where the sun is directly overhead. So that's why this thing's coming in at a right angle. The sun is literally directly overhead on June 20th. And up here in Alexandria, it's not directly overhead, and it makes an angle with the vertical. So this is vertical away from the center of Earth of theta. And I think historically for that place, it's 7.15 degrees or something. But this experiment can be repeated anywhere. And we have the radius of Earth. Because the parallel rays assumed, we have an angle here, theta, and we have the arc length, that's the north-south distance between these two places. And with that, and I'll put this name up for you guys, Eratosthenes. Yeah, with that, you have a nice geometrical relation, namely S, the ratio of the arc length to the circumference is equal to that measured angle divided by 360 degrees. Of course, you can do it in radians too, but we're going to do it in degrees right now. And that relation has as its only unknown, Eratosthenes is supposed to send someone down from Alexandria to count the steps or something, right? All the way down there. So if you know that arc length, then only unknown is R. So solve for R equals, and then, you know, plug in depending on where you did this problem, but like I said, one unknown, 6.37 times 10 to the 6 meters in modern units. That's not bad. And I already have a simple homework problem for us. Find theta for Fresno. Could be as easy as looking on a map. But yeah, find the angle that you're going to measure for Fresno. This was on June 20th, so this is June 20th. Could be as easy as looking on a map or a globe, but that's a good thing to get started with. And then you draw that picture and explain your thinking. Okay. So this is the straight up and down in the sun on June 20th. It's never directly overhead in Fresno, right? So it's somewhere there, and that angle that we're measuring is that one. Okay. Good. Yeah, I insist that we all know this stuff. I told these guys last week that I'm quasi-traumatized by the flat earthers. So we have to be on our game, right? So that was the one thing. Now the next calculation, and this is going to be good all the way through kinematics. The next calculation is just if you now have a spherical Earth, and that little distance there, that the hypotenuse is longer than this leg by h, okay? That'll tell us how much h is, how much you drop off as you head towards the horizon. Okay? So the farther out you are, the more the Earth or any sphere drops off there. And this one we can calculate just using the Pythagorean theorem. So we've got r squared plus L squared equals r plus h quantity squared by Pythagoras. And we expand this out. We have r squared plus 2r h plus h squared. We can drop those. And we're going to keep h much less than r. And so we'll just drop this. We'll keep the equal sign, and we'll get L is equal to root 2rh. And of course, we can solve that for h. The distance you drop off as you move out towards the horizon. What do we get here? L squared over 2r. Now, then I said, this one's difficult in practice because if you're at the level of the sea level and you're sighting out over the ocean, you get refraction depending on the condition of the air. So you can even have a mirage and a ship in the distance look like it's up in the air. Okay? So this one has to be used judiciously. But we also had a third version of this. I'll just walk this off. And that was what we ended with last time. Namely, I'm just going to repeat this picture a little bit smaller. Suppose we're on a mountain that's a height h, and we're sighting down towards the horizon. So now, we're on a mountain sighting down towards the horizon. We've got the h, the r here, and the L. In other words, we realize, I won't draw the L, it's actually the very same picture as that one. Okay? Just slightly reinterpreted. And what we're going to do with this one is ask ourselves, what is the angle under horizontal that we now experience? And that angle under the horizontal will increase the higher we are over sea level. Now, to do this in practice, maybe we need surveyors tools to measure very accurate angles. I think I can turn this into a homework assignment as well. So this is what I did last, and basically I'm using, because L and H are much less than the radius of Earth, I was using the fact that this angle I just identified there, because this is 90, I'm going to find that angle in there again. So I can use an approximation here. L is going to be approximately equal to S, which is equal to R times theta. And I made a substitution up there. And what do I have? H is equal to R squared theta squared over 2R, so 1/2 R theta squared, which coincidentally is going to look like the beginning of a Taylor expansion, right? But we could solve this one for theta. Theta equals 2h divided by r square root. So this one I think we'll do in radians. I want to make a homework problem out of this as well. Namely, what angles are we going to find if we use the known and accepted radius of Earth? If we're up on mountains on a coast, I'm thinking Hawaii, all the astronomers go there anyway, and the big volcano there must be 3,000 or 4,000 meters, 4,000 at least, right? 50,000 feet, close to 4,000 meters. Okay. So imagine you could go up there 1,000 meters at a time, 1, 2, 3, 4,000 meters. You would take 4 measurements, and then, you know, if you were physics, whatever, you could make a straight line graph. And the slope would be the, radius, that kind of thing. So let's make that a homework as well. I think that this is in the picture here. So homework, find theta, comma, in radians and degrees, or whatever it's worth. And convert and degrees, comma, for h equals 1,000 meters, 2,000 meters, 3,000 meters, and 4,000 meters. How about that? So, yeah, so that finishes this particular section that I want everybody to understand. How many people have heard about this stuff before? Very much at all?
Heard about the Eratosthenes.
There, exactly, yeah. So that's really classic, and I mean, we should do it someday on June 20th. We can do this, because we're all on vacation, right? But if somebody remembers, and then check there, and you know, it'll be very clear that you're getting the right angle, Good. So that is our, you could say, preliminary material. But we're actually going to get some interesting use out of this formula here, unexpected use, pretty soon. So, kinematics use. So, okay, I'm going to erase this. Everybody has it. And like I said, we have a couple of nice little exercises. Those will be on Friday. Oh, the way we do the homework is it's due Friday in the afternoon. So we have a last chance to talk about it in class if we need to. And then you can either put it in my mailbox downstairs or slide it under my door. The janitor always pick it up on my desk. Good. Okay, so I'm going to erase this. And the next thing is going to be free fall, for which I have a demonstration. Okay. See that one up there. Okay, in fact, I have a bunch of demonstrations. So next, free fall. Bring this out here. I have the famous hammer and the feather. I have a book dropped on. Not mine, but it'll provide that. Good. We're just going to do this in more just as a discussion. So the famous hammer and the feather, Galileo style, which one hits first?
Hammer, because their resistance.
Exactly. That's cutting the whole discussion to the point. So the hammer hits first, and on the other hand, you know, you could do a hammer, a feather, and a tennis ball. And at this close range, the tennis ball falls just like a hammer. If we were dropping the tennis ball from, say, the top of the library or something, it would slow down, right? The hammer would win. But yeah, it's all about the wind resistance, the friction, and unless you the point of this discussion is unless you eliminate that, you can never find a law of free fall. Okay? That's why these preliminaries are important. Like you could do a sheet of paper, and there's no telling what the paper's going to do because it picks up air and has all kinds of aerodynamics, right? Okay. So, you know, paper and feather. And if you do a more large paper move, right, it just floats around and does unpredictable stuff. Okay. So that's why you really have to eliminate the friction, otherwise everything falls on its own, so you can't find a law. Okay? So you eliminate friction to find the law, and by the way, I can't resist showing you guys, should have brought a decent sized book, but, oh, here we go, this will work. Composition book. So there's a way you can make a feather fall just like a hammer, and that is if you just put it, you know, it's not going to stick, right? It's not going to stick here, but marks get set. It falls like a rock. Okay, you can either do this, or you produce a vacuum, or you go to the moon, or do whatever it takes. But you literally just put it on this book here. It's not sticking, and it just goes down like a rock. So anyway, all these things have to be understood in order to find the law of free fall. So I'm going to give the demonstration right away, and then we'll do the kinematic concepts. You know, I could start doing kinematic concepts, but we've seen them before, so we're not total beginners. But this is a very nice idea that goes back to Galileo. So what Galileo did, once he realized this stuff with the friction and all, he needed to slow the action down. So he did an inclined plane, and he hypothesized that you're going to get the same law, and as you make it steeper and steeper, you know, it turns into true free fall, but you're going to get the acceleration this way. And the trick is, as you have these things rolled, some marbles rolled down a groove in a plank, the trick is to put something here that will make a little clicking sound as it rolls by. A little bell or whatever, something that goes clicky, you hear it. And you'll notice I've put these in increasing increments of distance, but I'm going to get even clicks. So even without stopwatches, he has a musical sense, he has a sense of rhythm, and as soon as these clicks are completely even, he knows he has equal times, and he can measure the distances and get a distance and a time law. Okay. So this is Galileo's inclined plane. Incline there, and he's rolling these things, and you know, it hits the first one, click, click, click. Well, we could do that with something that's called, so this is just the idea of something that's called the drop chord. And the drop chord is a string with a sounding board. And we're just going to put some clips on here. And since I know the answer, I don't have to try this 10 times, right? We'll put them on in increasing distances, and we're going to get the even clicking sounds. And let's see what happens. So I can do this in real time. I need a ruler. I've got a table here. So always wrap your string on something so that it doesn't get tangled. The bottom is just anchored with something so that I know where the bottom is. And then I put these clips on here. And let's see if this works actually. Guessing my distances. See what happens here. We'll do 4 of them. Should do the trick. We can do a second try if need be. Good. And then the soundboard goes on the floor. for an even rat-a-tat-tat. Once more. Was it good? Even? Okay. And so it's very even, right? Because we know the laws of nature. But you guys can see, since you couldn't see it on when I had it on the table there, but I'll rest it and do one more. You can see how I'm starting with small and getting incrementally larger. Okay. And once more. Okay, good. So there's your drop chord demonstration, and we're just going to label what it is we're doing. Good. So it's going to label it now. We'll put a little graph here. So these are our data for the successful drop chord experiment. We had the time and 0, 1, 2, 3, 4. And we didn't know what the unit is, but we know they're even. Okay, that's all we have to know. What about the distance fallen? That will be revealed. So what I had was 0, 10 centimeters, 40, 90, 160. And of course, if I just did that in arbitrary units, it would be 0, 1, 4, 9, 16. Yeah, what's the next number in this list here? Anybody? The next two numbers, yeah, 25. I'll put them in parentheses since we didn't do them live, right? So we get 25, 36. So that is distance times squared. Okay? So distance is proportional to t squared. Watch this. D over t squared is therefore equal to a proportionality constant. Right? That's what it means to have proportionality. But what are the units of d over t squared? Because we know this stuff already, I don't have to take it from scratch. So this is meters per second squared. And therefore we have a law of nature. This is the last time we get a law of nature this fast. Free fall is motion with constant acceleration. So therefore free fall is motion with constant acceleration. With constant acceleration. And actually over here, I should have characterized the free fall, and I'll put it here so we have it in our notes. Free fall, we just have to say no friction or sufficiently little friction. We know what's meant there, right? That all I had to do was put the feather on the book and I had free fall. So free fall is motion with constant acceleration. And yeah, now we can motivate all of our kinematics and start working our way through all of that. So the drop chord, this is a good one. Because it goes so fast. Did you ever build one of these? Go ahead and do it the way I did with clips. Sometimes people try to tie something on a string permanently, and it just turns into a tangled mess, right? So if you have clips and you have a ruler, you can always make it in real time. Good. So So this puts us right at the beginning of the whole science of kinematics and then laws of motion with the law of free fall. Motion, acceleration. Good, so I'm going to erase this, and now we'll start into the basic kinematic concepts. Also, so after we do this, this is kind of a review, but we'll do free fall. We can do some projectile motions. And I also want to do a review of uniform circular motion before we get into the more technical aspects. Because last year, I had a group, they didn't remember much about uniform circular motion, so it's better just to tackle that as well. But right now we'll do the kinematics. Go. And there's a lot here because if you weren't physicists, you'd have to learn what position and all those things are systematically before you can just look at this and say, aha, motion with constant acceleration. So we'll get the list of concepts up here and work our way into it. So our next topic is the kinematics, kind of taking it to the top. And we'll just do the list first. Position R. So actually we have to know something about vectors. Position in free space, we call it R. And we can do a number of different things. We can have an ordered triple, and I'm just gonna say what else we could have. We could also have X, I hat plus Y, J hat plus Z, K hat. We're just interchangeable with these kinds of concepts. So I'll just put here note on vectors. Vector R, magnitude, R without the arrow on top, x squared plus y squared plus z squared. We'll do a little section on vectors where we go more systematically. But for now, just to remind us. So yeah, you've got position, and since it's a vector, it's an arrow. You've got some origin, and you've got some vector, some arrow pointed somewhere in space. Good. We can fill in with a lot more about these, but this is familiar to everybody. So the next concept here is then displacement. Delta R. I could R minus R0. Something's been moved from one position to another. And in the vector world, say this is R0, and this is R, since we're going to be talking about motion some instant later, but not even this, is part of the trajectory. So then the delta R, by the laws of vector addition, is this one right here. Delta R. And since vectors just add like arrows, you've got your R0 plus delta R is equal to R. And that, of course, is identical to the definition up there. I start here. Actually, I start here at R0, and then I add the delta R. And then I'm at my final position. So yeah, when you have a difference vector, it always points to the final two. So there's your displacement. Yeah, what comes after displacement in this progression? Velocity, yeah. No surprises here. So you have position displacement, then you have velocity. And velocity is a derivative. So v is equal to the limit as delta t goes to 0 of r of t plus delta g minus r of t divided by delta t. And more simply, you have v is equal to t or dt. So now we have to say something about derivative of a vector. And actually I said it right up here. So the derivative of a vector is just like the ordinary derivative definition. Of course it is three derivatives at once. So if I go back to this here, it could be dx dt, dy dt, dz dt. We could have it in that form. And if I wanted the speed, it would then be the analogous version of this. So I'll put this under here. Speed v equals, now I have to bring in the magnitude of v, of velocity. And I'm going to do this. Square root of vx squared, vy squared, dz squared. Just to get used to some of the nomenclature. So that's all there. And finally, of course, I wanted to put it on one board, but maybe I'll put it down here. Finally, we have to get the acceleration. So three numbering here for acceleration. And we have acceleration is derivative of velocity. V of t plus delta t, t delta t equals ev. With all the same points about components, if you want to do it with components. So yeah, those are the concepts, and it can actually be interesting to go get there with a projectile motion. But so now we have all four of the constants that we need, and we want to go straight to constant acceleration. This is the most basic, and it's really the most important of all the applications. Although we gotta go far beyond it, but it's important. So now that we have these, we'll investigate constant acceleration again. And I will erase this. Let's see if we can get an assignment out of this. I think we can. So what we're going to do is constant acceleration in one dimension. And that'll just, we'll be able to generalize it, no problem. Constant acceleration, one dimension. And we'll just call it x. And so now we have d, v, dt. Actually, yeah, we'll do dv dt. We're just going to name it, well, A. A is a constant. Equal to constant. because of that, and I'm going to put this as a homework. Hold on. This one I'm going to kind of just work through, but you guys fill in any missing things. So because of that, we can say B equals B naught plus A times T. Right? That's just the antiderivative. And then we have dx dt is equal to v. And now we have that v there is equal to v naught plus at. And a simple integration gives us x equals x0, which is our integration constant for the whole thing, plus v0t plus 1/2 at squared. You'll notice if there had been no acceleration, x would just be x naught plus v naught t, right? So let's see, I'm going to turn this into. Okay, so this generalizes generalizing to free fall in xy. Actually, here's what we're going to do. In free space, we're going to generalize this to free fall in free space. Then we can say r equals r0 plus v0 t plus 1/2 a squared. What do you guys think of that? I just did it for one, but I could have done it for all three components. Okay. And if A is equal to G and pointing down, then G is just a constant vector pointing down. And so you orient yourself, you create your coordinate system as you need, right? So, but right now this is without. They're Cartesian, but we haven't specified any coordinates. So here's the always interesting homework problem. Prove that this motion is restricted to a plane. This is in 3 dimensions, right? But the motion itself is restricted to a plane. So prove, and the proof is actually really easy. If you start doing complicated stuff, you gotta actually just have to think it through a bit about what it means. The constant acceleration motion, so that's the motion we're talking about right here. Motion is restricted to a plane. And so now we have a nice assignment for Friday. Conceivably, no, today is Wednesday already. Yeah, so now we have a good set of problems, 2 problems for Friday, and Friday's lecture, anything I put on the board as a problem will be for next week. That's how we're gonna do it. What do you think? Are you not seeing the answer right away?
The plane is defined by 3 points. You're moving down in one direction because you have to, and then whatever you're moving in xy just defines a line. So that downward plus divine, you have a plane.
Yeah, you don't have to call it down though. This could be the acceleration of an electron due to a constant electric field. But yeah, you could, basically, if you think it through the way he's discussing, you can, come up with an adequate proof. But it's an important one, because then you guys remember from your other classes, we always do projectile motion in x and y, right? Or in 2 dimensions. So that'll be the proof for that. And perfect timing. So that's all we've got for today. And there's a good homework assignment for us, but we can talk more about it on Friday. But anything I assign on Friday will be for the following week. Good.